Comments like these are why I absolutely freaking love the internet. Well, hello everyone, welcome back to Zomboland Gaming. I am, of course, Zombo Skater, and we're back for episode number 8. It has been a while. I'm taking my glasses off because, good lord, these things hurt on my head. Anyway, yes, we're back with episode number 8 of Turing Complete. It has been an absolute minute since the last episode. I know, work gets in the way, my brain gets in the way. This stuff is starting to get pretty technical, and as a non-programmer, we're into the start of the start of the game where I don't know what's going on. So anyway, first things first, we're going to cover some of the changes that I had to do since the last episode. I believe it is, nope, that is second tick. I believe it is exclusive OR. So essentially, they just got rid of, they made this new input right here, and it got rid of my inputs and outputs. All I did was copy and paste it over. So that was a change that you might see. And then bit inverter, same thing. All it did was this brand new input, and it removed my inputs and outputs. So all I had to do was copy and paste. And then for some reason, up here in the CPU architecture, I essentially had to go all the way through the registers, all the way back up through Turing Complete, as they've added this right here, this little level screen, and then, of course, a component link to be able to link various different components in your computer to this so you can see it on the level screen, as well as, I believe my inputs and outputs were gone, too. Or specifically for the register level, I believe, yeah, we had like a little instruction input bit that was there. That was gone. So those are the only changes that have happened. Which is pretty darn nice because, oh boy, yeah, it was a disaster. Thankfully, I went back to my episode 7 and I was able to just watch through my episode 7. And you'll notice if you follow along, some of it's a little bit different. I basically cleaned it up a tiny little bit. To make it a little bit easier for me to tell what's going on and troubleshoot stuff, as I had some issues down here with some connections for like mainly register 2, and then the immediate register coming out. So yeah, okay, so that's that. So let's go ahead and get on into some comments. I'm going to read these off of my phone, so pay attention, not pay attention, bear with me as I do one of these numbers. Yes, I am looking at my phone. So first one is from Diomedes. These are going to be on the screen, by the way, somewhere around here. Yeah, this is from Diomedes. He says, I agree this program turns an educational program into a messy game that wants to intimidate by limiting wow, I can't word. Every single time we do these, I can't word. Okay, that wants to intimidate by limiting logical resources and testing space constraints. It's better to just bypass the play campaign and play with a sandbox or schematic hub. So we've noticed, I complain a lot about the lack of one-to-one realism of what the game's trying to get you to do versus a real CPU. But recently, let me shift tab here. Actually, I don't want to shift tab. I can just window out, and we'll go over to Steam. So this was back March, so not recently. This was March 18th of this year. The developer posted a little update about embracing realism and short-term roadmap, including this really good YouTube video. It's just a vlog, and he's just talking about the development and what steps they're taking and whatnot. But he discusses in there the criticism that's been made about the lack of realism versus, the puzzle nature of the game. And he talks about how he created the game mainly as a puzzler for people who like the games like Factorio and any kind of random puzzle solve games, and it wasn't so much about learning how to build a computer. I mean, obviously that's an important part of the storyline, if you will, of the game, is to learn how to work a computer, but that wasn't his main focus. But I guess he's always had it in the back of his mind as he wants to get closer and closer and closer to a full-out realism sort of deal. So that is actually coming down the pipeline, and he discusses in there. So I guess less complaining in the future from me because, well, he's acknowledged this, and he wants to actually work on making it more realistic and whatnot. So that's pretty darn awesome. Let's get back into the game now. But good. All right, so that was Diomedes. So, I highly agree. 100% agree with your comment. That's exactly how I felt up until that update, and he kind of changed my mind and my perspective on, yes, it is a puzzle game, not a one-for-one lesson tutorial deal. All right, now we've got Meepo. It's what I call a clean space. If I show you what I does, of course, that worked, but that's really ugly. Grammar aside, yeah, as you can see here, I could totally make this a hell of a lot cleaner, a lot more efficient looking, have my lines running in a much tighter space. Like I could have put my decoders up here and had them running straight down instead of having the 90-degree bends. But you know what? At the end of the day, if it works and it looks like spaghetti, meh, GG's, good job for solving the problem and figuring stuff out. You know, I play a lot of Factorio and Satisfactory, and let me tell you, part of the fun in that game is sometimes just creating a spaghetti bowl of conveyor mess. If you can troubleshoot it, and you can see where the wires are going to and from, hence why I color mine, who cares if it looks like spaghetti? Did you solve it? Did you enjoy your time? Did you have fun playing it? Good on you. Make a messy game. GG's. All right, I don't know how to pronounce this. It's on the screen. Knedilk, Minecraft Pocket Edition, MCPE. The reason they give you a NAND and not an AND is that you can build anything from a NAND, but not from an AND. This is supposed to be NAND to Tetris. Now, while I sort of agree here, as, you know, in the real world when you're building stuff, you know, single transistors, you know, yes, it's very much cheaper and easier to use a NAND to build everything else, right? However, there's more than one universal gate. You can also build all the gates out of NORs. So we actually saw that when I built my ALU. I mean, we didn't have a NOR bit, but we had NOTs and ORs. So I made the NANs, the ANDs, the NORs, the ORs. I made everything out of basically NOR gates. I just put two NOT gates in front of an OR gate. Boom, we got a NOR gate. Or, you know, or opposite, put an OR with a NOT afterwards. Then we got ourselves a NOR gate. And I use those to construct everything. And the other thing I really don't agree with on that statement is that in nuke school and college and all the textbooks and other things that I have over the course of the years, generally they're not starting you out with, this is how it's built, which is why we do this. Instead, it kind of goes on, off, on. You know, it does really, really, really simplistic things, right? So it starts off with NOT gates because you've got wire A to B, just is what it is. A NOT gate takes that input and swaps it around. And then it goes to an AND gate because that's the kind of brain waves, you know, it's the next easiest thing to think about. You have to have both to have something out. A NAND gate is just the opposite of that. And then it goes into OR, which is like, hey, you know, you can have either one of these, boom, there you go. You know, it steps you through. I mean, heck, I can show you here on this page in this practical electronics for inventors, which you probably can't see, but yeah, that's a NOT gate followed by an AND gate. You know, I mean, it's the way kind of, you know, it's presented in most theory books and most college textbooks and whatnot. And then they'll get into more of the manufacturing process of things, you know, with how it takes a single transistor, multiple transistors, the CMOS versus MOSFET, and, you know, all that sort of stuff to build it up, which is not presented here at all. It's not even an issue here, which is why I think most people were kind of like, why didn't we start off with an inverter, then go into an AND gate and an OR gate, you know? So, but I agree with your comment. You know, it is based on real life building of components. Yeah, NAND gate would be the way to go. All right, then we've got Obada. This was 6 months ago. I apologize extremely for not getting back to you sooner. And it looks like Legacy Beta also wanted to know. Legacy Beta with 2 3s instead of E's. Very, very nicely done. So yeah, he's right. Logisim is what I use, and that is, if we go to the intranets, so yeah, it's right here. It is cbirch.com. There's going to be a link down below for this. I don't know if I did it in one of my other videos. I'd have to go back and look. But this is the kind of play around silly program I use to build circuits and try things out or whatnot that I can't really do in-game, or if I'm making breadboard computers and stuff like that. I'll use this program. Like I said, link will be in the below. Obada, I'm very sorry for not having posted this a long time ago. Thankfully, it looks like Legacy answered that for you. But there we go. That's Logisim. And then we've got a very long one by Mina. The weird thing for an SR latch, as well as a full adder, is that it's symmetrical in a sense. The full adder is truly symmetrical in that there is no importance for the order of inputs, only their count. Very, very true. The SR latch, in turn, is symmetrical in the sense that reversing how you think about the inputs is exactly akin to reflecting the SR latch. So you could define the SVR, the set versus reset, so long as you realize the output is the opposite. Yes, exactly, very much so. If I wanted to make one side the set and one side the reset, it's all up to me. I just have to know that my Q and my Q naught are going to be swapped on the output. Got it. Very, very nice. As for the counting level, using the exact solution for double trouble is possible so long as you and that with checking that you don't have 4 gates by using the output from the part of the circuit. So this we're going to explore next episode because I want to dive in to that level and take a look at her idea here and see how it works and see if it's going to be a much better or cheaper, more efficient, or just, a cooler solution. All right, Chris Dieringer. In my copy of the game, the registers level does not have an input byte and an instruction byte. It says copy input to output, so on and so forth. You can read the rest of that. Essentially, what I think he's talking about here is what I discussed in the first part of this, the fixing of the level section. So when you come into this level map, a lot of the times after updates, you're going to come in here and you're going to notice that things like the inputs would be missing. Maybe the program is just absolutely gone, some sort of weirdness, right? So what you can do is you can come up to the switch schematic, which is the third icon from the left there. Click on it, and then you can just make a new schematic. And you can just come over to your old schematic and grab the multi-select tool and just select everything. Control C, come up here to a new schematic, say new schematic, name it test for video, like that right there. Boom, make it a name. Double click on it to open it up. And then once you're in here, just go Control V, and now we can paste this wherever we want to. And then, if we were missing our inputs and outputs, we can then connect our inputs and outputs up to them. And there you go. That should hopefully be the solution to your problem. If that's not, please let me know, elaborate in the comments, if I'm missing something that you were saying. But from the comment, it looked like that's what you were having an issue with, is that you had nowhere to put in an input. You had nowhere, because all of this stuff, the program was gone in the register section. You just had an instruction byte. So you wouldn't have been able to have inputted anything but manually, which is probably where your issue was. So hopefully that's the fix for you. All right, and finally, I love it. I love comments like this because on the internet, you can only get so much subtext and context from text. So you never know if somebody's being snarky, sarcastic, mean-spirited, rude, nice. Like, you don't always have 100% the emotion behind the person's comment. And this, I love it. I love it. Over 12 minutes and still talking and nothing. Nice gameplay. That was on my very first episode, a long time after that had been posted, where we had other episodes. I love it. I love that comment because I don't know if you're being just humorous or if you're being snarky or just being an asshole. I don't know, but it's great to me because, yes, I ramble on. I talk. We have lots of things to discuss. Just because it's a YouTube video about a video game doesn't mean we have to be playing the game. In the case of this, from the very start, I said we are going to discuss these levels. We're not just going to go, here's the solution, not discuss it, not talk about it, not learn together, just instant gratification for those people who can't figure things out. I'm not about that. This is one of the reasons why these videos take me so long, is that I have struggled with these recent levels because I suck at programming, especially brute force instruction set programming. So I'm learning all of this stuff. And I'm by myself here. I don't have anybody sitting right behind me. I don't have a college professor or somebody who's beaten the game or anything like that. I'm just trying to figure this crap out on my own. And so, of course, I get excited. I've learned, and now I want to share that little bit I've learned and hopefully learn more when I realize that I'm wrong about a lot of things. And I hope that the comments will help me learn stuff so I can become better and turn around to the next video and go, hey, somebody commented this, showed a better solution, and also taught me some stuff I didn't know yet. That's the whole purpose of the internet, in my opinion. Share knowledge with everyone so we can all become a little bit smarter and a little bit nicer. So whether that was snarky or not, I fucking loved your comment. All right. enough of that crap. Comments aside, flipping the page over to page number 2 because we are about to get into the actual levels. So we finished off in the last episode with Turing complete. We are done with CPU architecture, and now we are into programming. Now, we're not going to go over all 5 of these levels. We're just going to go over these 4 here because, this one I'm still trying to figure out how the hell I made it work. So I don't want to discuss it before I fully understand what I did to make it work. But getting on into it, add 5. Alrighty, okay, level log. Let's look at that. You have built your computer, but to win the competition, you still have to finish the maze. We're in a maze? Ugh. But since you don't know how to program it yet, you are not quite ready for that. You have no idea how not ready for that I am. So in the meantime, we will have you help out on the ship a little. I am now a deckhand, all right. Click on the Edit Memory icon on the program component to start programming your computer. Your computer should read an input, add 5 to it, and output it again. No need to worry about overflow. We don't really have the ability to have too much overflow anyway with this, so not a big problem. That'll come later. Notice that the immutable red register components have been replaced with a custom component with identical functionality. We must go to internets real fast. Immutable. What does immutable mean? We're learning together. Unchanging over time or unable to be changed. Oh, that's kind of what I thought immutable meant. Okay, all right. What unchangeable red register components have been replaced with a custom component? What? What? Were these... Oh, were these red before? Were the registers red before and like they put them in a spot so you couldn't move them, but now we can? Is that what it is? I mean, they look the same. Load, save value, output, always output. Whatever. All right, ignore that. Anyway, all right, so we got to input, we got to add 5, we got to output. And so the new things here are we have this little level screen, which we are just going to completely ignore. I'm not worried about it. And then we have our program has this new little button right here that looks like a little edity thing, right? So if we click on this, it shows us a binary editor. So we are going to come in here and actually change every last little bit of our program to do what we need it to do. So not to get too highly into detail, our basic goals are we want to read the input, and we want to add 5, and we want to output. So what we're going to do here is inside our program, you can see I have 177. So we know from, can we go to our instructions here? We know from our instructions here that having our little boom like this. There we go. So we have 177. This first part here is going to be part of our instructions that is going to say copy. We want to copy something. This part over here is going to be copying the input because these two are enabling our input. And this last little bit over here is to register 1. So that's what this is going to be doing. So our first part is 177. So if we take a little step here, you can see we've now enabled the input. We've got the 153 value coming down off our bus, going into register 1. And we have a register 1 because we are in the copy section. And if you're not quite sure about what's going on here, excuse me, good Lord, go back to the other episodes, episodes 6 and 7, I believe, and that'll show you how we built all this and what the register is here. This little decoder. We can go to our component factory real fast. That is the conditional. That is no, that's not what we wanted. We're backing out of everything. No. Okay, let's go back into Component Factory, switch schematics to our decoder. So yeah, that's what we built here. So this right here is taking the 128 and the 64-bit, and it's making a decision to immediate, calculate, copy, or a conditional. And so that's what we're doing here is 177. We've got the command to copy. Boom, right there like that. So this is our copy command, so we're not disabling our A3 to 8 decoders here. And we've got our signal coming down the line to save to register 1. So now we have this input value is being saved to register 1. Next step in our program is we're going to immediate a 5 value. Now, if we follow our immediate line here, which let's step the program to step number 5 there. You can see now we have this immediate line turned on, and it is coming over here, turning on the switch to allow our number 5 to come all the way through, down the bus, all the way back down around here, coming back up directly into input register 0 through this little OR switch that's enabling the save to register 0. So cool, we have our 5 now, and we have our input number. So the next step is going to be copying this 5 value down to register 2. So now the input we could have stored in 2 or 1. You could have picked one, right? So whichever one you picked, either store the input in register 2 or store the input in register 1. When you immediate this value to register 0, when you go to move register 0, you want to move it to whichever one you didn't save the input to, so that way you have both numbers. So in our case, we're going to go over to register 2, which is what this value is right here. And I don't believe I actually... Do I have that one saved register 2 like that? No, I don't have it saved. You can actually create all your stuff here. We'll discuss this here in a little bit, but just suffice it to say, when we step our program through to 130, you're going to see our copy is back on. We've got the value of 2 coming down here, which is then going to register number 2 to save. And then we also have this coming over here to register 0 to load. So we're taking that 5, putting it down into register number 2. Whoo! All right, so now we have our input stored in register 1. We have our immediate value of 5, which is what we're wanting to add, stored in register number 2. So the next thing to do is going to be our add function, which is going to be our 68 here. So when you notice this 128 and 64 bits, only the 64 is on, we are now in a calculation mode. When only 128 is on, we are in copy mode. So yeah, there we go. So we're going to go ahead and do that. So let's step it on through. So now we've added that into our ALU, I believe. Nope, it started the program all the way over again. There we go. All right, there we go. So now we have our 153 plus 5 gives us 158, and it is now coming here. However, it's just coming out. It's in register 3 because that's the way our ALU is set up, that when we're adding or subtracting or nanding or noring or anding or nanding or one of those things, right, out of our ALU, it just automatically gets saved into register number 3. So now that it's saved in register number 3, the final step that it asked us for is to read the output. So our next part of the program here is going to be taking and copying register number 3 to our output. So these two right here, the 2 and the 4-bit is going to be enabling the output, and the 8 and the 16 is going to be register number 3. And so we'll see that right here. Kabam. And you heard the little ding. The little ding means we won the prize. So let's just go ahead and step this through all the way. Bam, 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 bam. And it's going to go through 32 tests where it's putting that out to the output. And it's going so damn fast, you actually can't see it there. Bing, 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 bing. Boom. Yes, so now we've added a type of architecture to our stuff here. And we actually have some manual things that we need to read eventually later on. But yeah, so there we go. So simple as that. I'll leave this up on the screen so you can see it. We're basically inputting to register 1. We're immediating 5, taking register 0 to register 2, adding register 2 and register 1, which gets saved in register 3, and then we're putting register 3 on the output. That is all they wanted us to do. So that was called add 5. Now we're moving on to calibrating laser cannons. Let's move all this down here. Oh, and we actually have some stuff on the level screen now. All right. On our ship, we naturally shoot incoming asteroids with lasers. In order to calibrate said laser, we want you to calculate the circumference of the asteroid using an advanced equation. 2 times pi times r. We don't have decimal points in here yet. Our computer is not geared towards this. Thankfully, r is the input, and you can approximate pi as 3. Send the answer to output when it has been calculated. Also, you now have access to assembly programming. It allows you to add names for instructions, so you can add, for example, type add instead of inputting 68. So this is pretty cool. So what we're going to do here is we've got our program down here, and then we've got our copy component link that we showed earlier that we can link all the different stuff and things. But then when we come into the assembly editor, it is no longer a binary editor. Now we're actually going to type in commands. And if you want to, go ahead and pause the screen there because this is the code that I've built for this. And yes, it looks like code. However, it's just flat out instruction sets. We are still just brute forcing our computer with machine code, essentially. So what we've got here in the assembly editor is we have the ability to come in here and just like any kind of code, we can just type, right? And so we could type all of this stuff out completely. Like, we don't have to have any kind of assembly code here. We could type in what we want every last little thing to do. But an easier way to do is this little add button down here. We can click on add and we can actually create our own little assembly codes, name it whatever we want, save that, and then whatever that name is what we're putting here. So I've gone through and I've made pretty much all the functionality of our computer. So the ALU, we've got our add, our subtract, our and, our NAND, our OR, and our NOR, and it puts it all in alphabetical order, so you can see it down here. And then, because I want to be able to go from the input to all the individual registers, from each individual register to the other registers, and then to the outputs and whatnot, that's what I have down here. So you can see we've got input to out, input to register 0, and if I click on it, you can see it's got it all set up. So now I can just type in underscore to underscore register 0, and that's just going to pop that in there for me, so my machine is going to know I need to put this binary on the line. And then for the conditionals, so I'm a nerd. So if we go to our component factory here and let us go to switch schematics, and we're going to go to conditionals. So this is our conditional circuit, right? We kind of got an understanding of what this does in the episode that I built this in. However, I wanted to dive a little deeper. So we are going to take a look at a very nerdy spreadsheet so you can see why I named things the way I named them. Essentially, if you're a programmer, you would think of a lot of this stuff as the jump stuff in a program. I don't know those things. I'm learning them, but so it's called a conditional, and I did math and spreadsheets and stuff. So let's go over to the spreadsheet. Welcome to the world of my brain. So yes, I typed in, well, copied and pasted a bunch too, all of this stuff. So we know our circuit has these 4 inputs, right? It's got a 1-bit, a 2-bit, and a 4-bit. Not 4 inputs, 3, right? So we can do the binary for that. We're going to have 000, 001, 010, 011, blah, 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 right? But what did those mean on the conditionals? Like, what does that give us for an output? So what I basically did is I took our 8-bit binary here, because we need that for... Oh, come back, screen, there we go. So right here, if we look at this, condition is going to be these 3 bits here, and then this is going to be our input that's going to be coming from register 3, or is it register 4? Let me see, where's our conditional coming from? It is coming from register 3. So yes, so these 8 bits here are going to be whatever is felt on our register 3. These 3 are going to be what's coming from our actual instruction code. So now back to the spreadsheet. So what we have here is this conditional I've just set up in binary. This is every single possible sequence of what can go through our conditional circuit. So in the case of this top section, this is the always off section. So if you have zeros on your instruction set in the 1, 2, and 4-bit place, and you have nothing in register 3, then your circuit's got to be off. Your conditional will be off. And as I inputted it down and actually went through, I went through here, and we can see this right here, right now on our screen. We got nothing on there. There's nothing. Now, if I take and I add a 1 to the input, you can see the OR is made, but this OR is made, but then we can not it. So it's not going to an AND, and it wouldn't matter anyway because we don't have the other side of the AND. We're getting no output. And this holds true for like everything, right? So I then went through all of the different scenarios in the case of like condition number 1. So this is going to require this AND to be made. So it's currently on right now because both sides of the AND are made. But watch what happens. Oh man, I actually inputted something. This whole OR circuit turns off. And this AND circuit will never turn on because this is not made. Right? So I went through and I essentially diagnosed every last little thing. And then I came up with these portions of a conditional. So if you've got nothing on your instruction set, no matter what the input is from register 3, your conditional is always going to be off. If you've got a 1 on your instruction set, then you're only on when register 3 equals 0. When you've got a 2 in binary on your instruction set, it's on when register 3 is equal to or greater than 128. If you're 3 on instruction set, then you're on if register 3 is equal to 0 or you're equal or greater than 128. If you're a 4 in binary on instruction set, you're always on the conditional. 5 in binary on the instruction set, then you're on if register 3 does not equal 0. So basically the only time it'll be off is when it equals 0, otherwise it's always on. 6 in binary, register 3 has to be less than 128. Not less than and equal to, less than 128. And if you got a 7, then it's on if the register is greater than 0, but less than 128. So essentially 1 through 127. So those are kind of cool things to know about your conditional circuit. And we'll explore that probably later on when we're building our own stuff. But yes, I am a nerd and I went through and I did all of the legwork all the way down to figure all of this out. So you can thank me later. Anyway, closing out. All right, back to our circuit. Anyway, so that's conditionals, right? Good Lord, did we ever get off a track? So we're going to use those to our advantage in this one, and mainly for when we're coming up with our instruction sets. So like we see here, I've made my my instruction sets, good Lord, assembly code. So you can see here now how I've named these. So condition is equal to 0, that's the E, or equal or greater than E, GRT, because I can't place symbols and things in here other than an underscore, 128, right? So I could use jump names for these, like JMP or JE and whatnot, like JMP would be condition is always on, JE would be condition is equal to 0, right? But I didn't do that because I don't know those things. So anyway, long explanation short, if you want to know more about these, I can show the entire set here of how I built everything up, but it's pretty self-explanatory when you start going through it. All right, so what this wants us to do is it wants us to take 2 times pi times r, where they're going to use pi as a 3. Well, that gives us 2 constants, 2 and 3, so 2 times 3 is 6. R, however, we can't multiply with this computer. We cannot do that. That is not a thing that is possible with our current computer setup. However, if you go back to old school, then multiplication is just a hell of a lot of addition. So like, 3 times 2 would be 3 plus 3. 3 times 7 would be 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3, right? So that's essentially what we're going to do here inside this computer. And now I need to make sure I have, I took a long time to come up with this. It's very small, I know, but I had to work this through in my nugget over the past like 2 weeks here, because I'm a big dum-dum. So yeah, so what we want to do is we're going to do addition, right? So we know we have the constant of 2 times 3 times r. So what we're going to do here is we're going to take the input and we're going to stick it into register 1, or 2, if you want to stick it into 2, just be aware of which one you're sticking it into. And then what we're going to do is we're going to take that register 1, and we're essentially going to copy it down to register 2. So now we've doubled it. 2 times the number there. That's our first, because 2 times anything is basically that thing plus that thing, right? It's addition, right? When it comes down to it. So we've got our first number there has been multiplied twice. And then what we're going to do throughout the rest of this is we're essentially just taking register 1 and register 2, adding them together, taking that output, which is stored in register 3, sticking it back up into register 1, leaving the original number that we want to add over and over and over again in register 2. So we're just going to keep doing that as many times as we need. In the case of this, it's 3, right? Is what the number value is. So we got the initial value multiplied by 2, multiplied by 3. So we're adding 5 times, essentially. So what we've got here is we're going to take register 3, and we'll see this when I go through it. Register 3 back into register 1. Then we're going to add it again to the original value. Then take that added value in register 3 back to register 1 as the new value, add it to the original value, and just keep going through. And that's how we're going to basically brute force this out. If you need a bigger explanation, I can type this kind of up in the comments, kind of, to show you the math behind it. But just suffice it to say that it's essentially going, this is R, and then we're adding it to R, and then adding it to R, adding it to R, adding it to R, adding it to R to get our 2 times 3, which is 6 times. In this first example, it's going to be the number 1. What is 2 times pi times 1? So 6, right? So here we go. So we can actually step this through. Also, if you notice on the assembly editor, these are the linked components. So if we click on the link button here and you see all these little thin blue lines, those values are actually going to change in here when we step through our program. So as you can see right now, we've got our 1 on the input, which I believe I've got. Yeah, the input is number 1. I thought it was number 1. Oh, I don't have a value on the input here. So we've got 1 here. Oh, 1's our program code. So we've got number 7 is going to the program code. So this value right here is the program code, or sorry, the binary counter. And this one right here is register 1. So we've stored it there. And let me see if I can't, I wish I could zoom out of this window. I wish I could minimize it, but I can't. So we're going to kind of keep ourselves a little bit like this so we can see what's going on over here. So we're inputting to register 1. Step it through. We're going to take register 1, and now we're going to store it into register 2. So now we have register 1 and register 2. Then we're going to add them together. So you can see that 2 value is coming around and getting stored in register 3. We're going to add register 3 back into register 1. So now you can see we've got 2 is now stored in register 1 with the original 1 value stored in register 2. Add it again, which is going to make a value of 3. We're going to pop that 3 up into register 1, add it to 1 to make 4, add it again to make 5, and one last addition to make our 6, which 2 times 3 times 1 is 6. Now, this is going to want to do this 42 times. Oh boy, but we're going to go through it one more time. So the next one is 2 times pi times 8, right? So the same thing that we're doing here is we're going to go 2 plus, or 8 plus 8 plus 8 plus 8 plus 8 plus 8 makes 48. 2 times 3 is 6. 6 times 8 is 48. The math checks out. And here we go. We're going to watch this happen. So you got 8 in input 1, which was from the input. You got 8 now being stored in register 2 because we've copied it. Add them together to get 16 in register 3. Move register 3 up to register 1. And now we're going to add 16 plus 8, which is 24. Move it on up. So now it's 24 plus 8, which makes 32. 32 plus 8, which makes 40. 40 plus 8, which gives us our final number and our 6th addition of 48. There we go. So that's pretty much as simple as it really can get without having any kind of floating points or decimals or any of that kind of sort of deal. We've brute forced pi and circumference. That's pretty cool. So let's go through it real fast. You know, we could actually probably zoom it real fast. There we go. All right. So if you have any questions over that, definitely leave comments below. I hope that made sense. We're just taking, instead of multiplying, we're adding, and we're just doing that by taking our values and popping them back in and then adding them to that number 2 register, which we never touch. All right, a level editor. So now we are on to Spacial Invasion. This one, I am going to be straightforward and honest that I needed freaking help on this, and we are going to talk about the person that I got help with for it, but I did attempt to do this on my own, and it was miserable. So let's go through the log here. We've got the cargo hull has become infested with space rats. We have hooked your machine up to our advanced robot, and we want you to program it to shoot the space rats with lasers. Be aware that the lasers can only shoot when there are no other laser beams already in flight. So if we shoot, that means we can't do anything else with shooting until that beam hits a wall or a bug or something. Check robot page for instructions on how to program him. There is a link to that page in the program editor as well. Now, here's where I got myself confused, not on this part, but on the things that I needed to use internally in the program, because I completely skipped some stuff in the earlier episodes. But anyway, robot page. So it says, this screen shows a robot and his surroundings. This is obviously a different level than what we're looking at, but same. So the robot sees one tile ahead of him. The name and ID are shown up here. This ID number is also the computer's input. So what we'll see here in this little orange value is going to be the input that is going to tell us if there's a wall or a robot or just a tile ahead of us or whatever, right? And then down here we have controls. So we're going to be able to input these in as immediate values to make our robot do something. So 0 will turn him left, 1 will move him forward. Oh, I got the hiccups. 2 will turn him right. 3, enjoy the moment, or essentially wait, don't do anything. 4, use an action, which we currently don't have any actions other than shooting, which is number 5, shoot the laser. So, all right, so we can use our arrow keys and tab and enter to play around with stuff on our own, so we can kind of give us an idea of how this thing works. But first things first, assembly. I completely avoided reading this, and this is what made me super duper struggle with this level until I read it. So you can use a max of assembly codes and numbers to get bytes, blah, blah, blah. Anyway, whatever. Skipping all that, you can read that on your own time while you play the game, but here's the important part. Label assigns a name to the byte offset of the line it was inserted on. This is especially useful for naming jump destinations. So that is the key important part of this level that I completely bypassed when I first started trying to program this and kept dying and dying and dying and dying. You want to create what's essentially like a loop in your program and jumping to certain points based on certain conditions that are being made, as we're going to see. So remember that. That is super important. So anyway, boom, close. There we go. All right, so right away, nothing's changed in any of these. As you noticed, we have our computer. We're not adding any more components. All we're doing is changing our program. So here we go. So you're going to notice on top here, Storm Surge. Yes, I labeled and named this because this is not my, well, it's my fix for his original design, because he put up this level prior to a couple updates, and some things have changed in the way he designed his program. Plus, I realized there were some things I could remove. But before we go look at that, you're going to be able to either step through your program here, using the normal typical step throughs, or I can use the arrow keys like you see me moving around here, right? So I can move my arrow keys to move around. I can use the tab button to shoot, and you're going to notice, boom, 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 boom. Yeah, shoot things. Let me turn around. Let me shoot some more things. Boom, boom, boom. Oh, I died, right? Okay. So we have an idea of what we need to do with this guy. We need to shoot all of the little Space Invader-y rats on the screen. And now I was kind of struggling with this. I was doing some stuff here where I was moving my character, getting him around the wall, coming up to a point, and then trying not to die from these. And then I would just sit here and start to shoot, right? So we've got all these aliens coming at us. And then I can move forward a little bit, turn left, move up. Oh, actually, I don't want to move up. I want to turn left, move down. Oh, and turn around, and then start shooting these guys. Boom. Oh, God. This is getting dicey. They're getting too close. Oh, I got him. I got him. Oh, yeah. Look, 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 look. Yes, yes, yes. We're playing a game without actually playing the proper game. Boom. So, see, I won there, right? So, I kind of have an idea of what I want my character to do. I want him to move. I want him to shoot. I want him to get in line with the robots or whatever, or the rats. And so I did that. And I kept moving my character out around this wall. And by the time he got himself into position and he was just shooting, he would die every time because the coding that I had done was just absolutely miserable, and basically gave the rats an advantage. Because what happens is every time you move in the game, be it your action, your tab, or making a move left, right, forward, the rats will immediately move one more space after you've done that. So that was something I wasn't paying attention to, is that I needed to make sure that my move was going to also keep me out of trouble from dying when the rats did their move. So now also you can tell, let's go ahead and step this through. Boom, boom, boom. I'm going to quickly get this all the way down to us, because this is going to be a key important thing before we get into our discussion here. Oh my God, this is taking forever to get all the way down. I want them to get right in front of me so you can see the value right here. So you can see up at this top corner, it says 33 space rat. So that 33 is the important value to us. 33 is that there is a rat in front of us, and that's going to become important. So now what we're doing here in my program, and actually let's take one more step back. So if we go to Steam here, and we go to the community guidelines and the community, not guidelines, guides, Storm Surge, 100% guide. If you get stuck, some of this is a little bit older and may require you to do some extra work to make them work with the current update, but it's still a great place to start to be able to go, what the fuck is going on? I have no idea. I'm terrible at programming. But he has gone through pretty much every single level and has a semi-okay, smallish description of everything. I am scrolling all the way down to this current level. As you can see, he's done everything here. Oh yeah, look what I noticed. He actually used JE, JG, so, you know, jump greater than, jump equal, jump greater than, and equal. So he actually used jump terms for that. Calibrating spatial invasion. All right, right here. So yes, so his values that he has here are based on an older version of the game. Plus, look at this. He said I used 120 lines of code. I think I was at like 90 something on mine before it was just like, this is terrible. I'm giving up. This is way too big. I shouldn't be having to brute force 90 lines of code in order to get this stupid guy to shoot rats. So I came in and looked at this just to see what he was kind of doing and why, and learn a little bit. But the values he has for his immediates are based off of an old robot program. So those don't work. But yes, Storm Surge. If I ever get monetized, my guy, you were getting a cut of the proceeds for this because you have saved my bacon. So yeah, anyway, we've kind of used this program a little bit, but not all the way. All right, let's get into the program. So what we're doing here is we know, let's stop this so we can get back to the beginning. I found out that, look, tab, I can shoot, can I tab? I can shoot that piece of wall out. Like, let me get out of the way. See, you can see that that wall is gone now. Oh, cool. All right, first step. So what we're doing here is we're immediating. Why do I have all those there? We're making an immediate value of 5 to get our guy to shoot. And the way that you have to immediate, right, is that he doesn't just do something. You need to have that output. It's the output that makes him do stuff, and I believe it says that right here, right? Send output to control the robot. So we're going to immediate a value of 5, which gets saved into register 0 here. That's just how our immediate value goes. And we're going to read that register 0 out immediately. We're going to put it into 0. We're going to read it out. So that's going to make our guy shoot. And then we're going to move forward to put ourselves inside this little block spot here. And then, we're going to media to 1, and then we're going to read it out on the output. So that way our guy knows to move forward. So there we go. So we've done our first 2 steps. We've shot our gun. Boom. And then we've moved forward. So now we're in between these blocks here. So now I really don't have to do anything, right? I've got nothing to shoot. I know that if I shoot a bullet, it's going to wait until that bullet hits the wall or hits a rat before I can do anything else. So I don't want to shoot. So what's happening next is we're going to set up a jump area and a little conditional to tell our guy what to do for us while we wait. So this label value is setting our jump condition, which is going to be a wait to pop us back into here. So 3 is our value for, if we go to robot controls, 3 is the enjoy the moment, the wait section. So we're going to say, okay, you've moved forward, now wait. So we're going to put the immediate value of 3, read it out, and then we're going to go input to register 1. So what this is doing is we're going to have an input here. We're going to put it into register 1, and then we're going to immediate a value of 33 into register 2. So we're going to read it on 0. We're going to put it in register 2. What this is going to do is now this value up here, this little value that we saw here, what my guy is looking at is the input. So what we're doing is we're going to be looking essentially for 33 because we know that these rats are a value of 33 when our guy can see them. So we've immediated a value of 33 into register 2. And we're looking for the input, which in the case right now is 0. And so then we're going to subtract those 2 values. And then that's going to give us our 2 conditionals of E equaling 0, which would be 33 minus 33 is going to be 0. So that's going to go, oh shit, there's a rat in front of us, shoot it. Or if we're anything other than 0, then we're going to wait, because our condition statement would be something else minus 33, which could be anywhere in that range of 0 to 255, right? Minus the 33 value. So what's going to happen is you'll see us, and we can kind of step through this a bit. So we've done a 3, we're waiting. Now we've taken the input, which right now is 0, and now we're going to take a 33, and we're going to put it on register 0. And then we're going to read register 0 to register 2. So now I've got a 0 from our input, 33 that we just immediated, and now we're going to subtract the 2. And you can see that's going to give us a value of 223, which register 3 is going to come up here to our conditional statement here. And right now, if we go to the shoot phase, which shoot is just going to be a jump portion, right? I defined the label for shoot later on because that's where I want to jump to in the case of me needing to shoot again. But so we're going to look for the condition to shoot, which we're not equal, so we don't shoot. So then we come down to wait, and the conditional is now made here for waiting because the output is always on. So then what's going to happen is we're going to jump back up to the 3, and now we're going back through the wait procedure again. So our guy is just going to sit here until these bugs get going. And this loop program is just going to keep happening and happening and happening all the way until, I'm going to let this go, all the way until these bugs get in front of us. And then we'll show you what happens once the bugs get in front of you. Stop, pause. All right, okay. So now you're going to see that we have an input value of 33 coming to register number 1. We've got 33 in our register number 2. So as we step through, we're going to put that 33 back into register 2. We're going to subtract, and now you can see we have a 0. So now when it comes down to our conditionals, we're going to make the shoot conditional. Boom, it's made. So it's going to move us on to step 15 because we've jumped to shoot. And now we are going to use the number 5 to shoot. And then we have to register the out, right? We need to tell our guy to actually shoot. And then we're going to once again take the input value here and we're going to move it to register 3. So now instead of needing to check for if there's a bug in front of us and a condition to either shoot or wait, now we're just going to take register 3 and just look for our conditional. So we're going to come right down and we're going to go the input directly to register 3, and we're just going to put register 3 straight out to this conditional. And if we don't see a 33, if we don't have an equals 0 statement, then we're not going to wait and we're going to shoot again. So we can see our guy is just going to keep shooting. And then this is just going to repeat over and over and over again, you know, until boom, bugs are back. Now we're in the shoot section of the jump program. And then we go back to waiting again. And now we're in the shoot program again, waiting again, back into shoot again, and donezo. So I hope that made sense. This took me so long to figure out, mainly because I didn't understand the jumping portion of the programs. But it's just shoot the wall, move into the wall. We're going to start a wait program where we're going to take and look for, we've put this value of 33. We want it to equal 0 with whatever's on the input. So that has to be a 33. If it equals 0, you shoot and move to the shooting command. If you don't equal 0, then just keep on waiting. And then once you get into the shoot command, you shoot. And then you want to check to see, is there something in front of me to shoot again? No. Okay, go back to the wait. Yes. Okay, go ahead and shoot again. So on and so forth. So hopefully that made a little bit of sense. I hope. It took me forever to figure that out, and thanks to Storm Surge, and you know, I had to like correct his program with updated values, and he had a couple weird things there where he was sticking his 0 immediate value into a register for no real reason. I didn't understand what he was doing there, but you know, I removed it and program works just fine. So it was a complete unnecessary line of code. But yeah, whoo, Spacial Invasion. Moving on. The last one for today. Like I said, we're not going to do masking time. We're just going to do storage cracker. The security access door to the storage room is broken, and it keeps locking our old janitor inside. The door keeps changing the passcode. We need a program that can recover the passcode at any time. The easiest way to find the passcode would be to try all combinations until you find the right one. Although the broken mechanism does make a weird beep when your guess is too high. You might be able to use that to your advantage. You win this level when you output the correct passcode. No output will fail the level. Additionally, the input will be 1 after a guess that was too high and 0 otherwise. All right, so this is actually relatively simple. What they're basically asking you to do is like think of an old, tumbler lock that has like the four, not tumbler lock, well, I guess it is called a tumbler lock. Hell, I don't know what locks are called. I don't know. You know, a 4-digit padlock that like has the little scroll wheels on it. If you wanted to like break one of those without just, using, lock picking tools, or a hammer or a pair of channel locks, then you would, start off with 1111, and then you go 1112, 1113, 1114, and you just keep going all the way until you finally got to, either 9,999 or, whatever number actually opened the lock. That's the same thing we're going to do here. So in binary, we're going to start off with 0, and we're going to work ourselves all the way up to 255. And that's actually really simple for us to do here. So once again, we're going to get into our program, and it's a relatively simple program now that I understand kind of jumps or whatnot. And the jumps don't have to be an actually defined piece of assembly code. It can literally just be a, hey, jump back to this point and keep going kind of deal, right? Which is what I ended up doing here. So we're going to start off with a value of 1 that we're going to immediate into register 0. And then we're going to take register 0 and put it into register 1. So that way we have that immediate value ready for us to be able to use. That's the first step. That's our starting off. Now we're going to actually start what I consider our main portion of the program, which is where I say label begin. So we're going to take register 3 and we're going to read it on the output. Register 3 has nothing in it. We didn't store anything in it yet. It's just going to be a 0, which is kind of what we want because that's our very first number. So if 0 happens to be the passcode, woohoo, bully, we're done. However, if not, you're going to add register 2 and register 1. Register 2 has nothing in it right now, so it's 1 plus 0 equals 1. And then we're going to take the stored value, which is in register 3, put it into register 2. So now we have 1. We're basically always going to be adding 1 to this. So register 1 is just going to be set at 1. Register 2 is going to be the added new number. So then you're just going to keep repeating that. Register 3 to register 2. You still got that value saved in register 3. You just also copied it over to register 2. So you're going to read that register 3, which is going to be a number 1 in this case. Did the passcode work? No? Okay, move on. 1 and 2 added together. That's going to make a number 2. Read it. Did it win? No. Take register 3, stick it back into register 2. 1 plus 2 makes 3. So on and so forth, over and over and over again until it meets a condition of on, and then it's going to reset the program. So we can step this through right here, and we can go, boom, add 1. So we're going to immediate a value of 1, which is right in here, coming all the way over to our immediate line, getting stored in register 0. We're going to take register 0 and put it into register 1, so we have it for later use. That is going to be our addition number. We're just going to keep adding 1, and then we're going to start our program, which notice it just skipped right over label begin because that's just kind of a placeholder just saying, hey, this is where the program begins. So then we're going to read register 3 right here. We're loading. That's the orange line, loading register 3. We're enabling the output. 0, cool. Apparently that wasn't the win. And now we're going to add register 1 and 2, which 1 plus 0 makes 1. Gets stored in register 3. And now we're going to move that register 3 into register 2. So we have it for extra use later. And now we're going to begin after a conditional is made. So did this make the, is 0 our answer? No. Okay, let's go back again. Register 3 out. Now we get the 1 out. Now we're going to add 1 plus 1 makes 2. We're going to take that value, store it back in register 2. And then we're going to check and see. Nope. Okay. Register 3 out. Is 2 the answer? So on and so forth. Boom, 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 boom. Over and over and over and over again. This takes a while, because not only does this take a while, it's a random arbitrary number. So in the background, you don't know what number the passcode is going to be. The game is doing that in the background. Eventually, it's just going to go bing, like you just heard it do. And that's whatever number it was. That's just whatever number the passcode was. It could be any number from 0 to 255. The game has picked it arbitrarily. I don't know what the value was. Hell, I can't stop it fast enough to figure out what it is. I think the first one's like 206 or something like that. But yeah, there we go. Oh, 206 was the second one. So yeah, so it's pretty like relatively simple. I mean, all we're doing is counting. This is really all we're doing. Is we're just taking 1 and adding it over and over and over again. So we made a count up adder computer. That's what we did. Oh boy. Good grief, that was a whole lot of stuff and things. So I hope a lot of that made sense. Let me tell you what, this next few levels are going to be mind-numbing for me, especially once we start. The CPU architecture 2 is probably going to be fine, because all we're going to be doing is adding like multiplication and division and floating points and all that sort of stuff. I'm hoping maybe that's in functions. I don't know. But that's going to be getting back to adding hardware, which I do know, sort of, for the most part. Not really, but we'll get there. It's the programming that my brain struggles to deal with, and I don't know if anybody else feels the same way. But guys, it's been a long episode. Thanks very much for watching. Don't forget to add more comments and tips and tricks and knowledge base and all that sort of stuff down below. You know, even post links to your versions of solutions and whatnot. I'd love to see like spaghetti messes or, you know, really refined, efficient, minimalized versions of them. I love that stuff. Definitely the programming. Please post your programming links to me so that way I can learn and understand better about how to program these things. Like I said, thankfully we're on the instruction sets, the assembly language, so it's a little bit simpler than the ifs and thens and ors and all that sort of stuff that we see in like C++ and whatnot. But yeah, whew, yeah, that was a good episode. That was a whole lot. We covered a bunch of information. Not really, 4 levels. Anyway, guys, thanks for watching. Don't forget to like, subscribe, comment, share with the universe, and I'll see you guys in the next episode. Ta-ta for now. Bye.